Okay, we're in the master control room now, and I'd like to introduce you my computer programmer who's the brains behind the machine. This is John Wells. And now we're going to look at the actual device that creates the heavens. And now right over here is the computer readout, the digital readout. All these little numbers tell the plotter where to go, where to draw the stars. And each one of these areas is what they call a buffer. That's right.
Right.
And it collects that much data and then goes on to the next, and after it's collected that, it starts drawing on this machine right over here. Okay, and we'll come right over to this is the plotter that creates the stars. And this machine is actually now drawing for 4 hours just half the sky, the southern hemisphere. And it's just about ready to draw the Orion's belt and the brightest star Sirius. And maybe we should open this up so that we can see this. Can I open this up? Okay, we'll just open this up a little bit so that you can see the machine drawing it. Now the XY coordinates, or any drawing, you know, like those little slates that you can turn one way and turn the other way, well this, the paper moves and the stylus moves back and forth to get your XY coordinates to draw any picture you want. And we're just coming up now on Orion. And this can do multicolor drawings and with what accuracy? What's the accuracy on it?
1/1000th of an inch. This on the back wall was produced by this plotter using ballpoint pens, 4 pin colors. And that's an actual original off of the plotter itself.
I'll name some of these stars. Oh. Oh. Okay. Now we'll close this down here so that the air doesn't get to it. This room that we're in, the noise you hear is the air conditioning and the coolant of all this computer equipment that we've got going here is the prime computer, storage tapes. And if you look at this is one of the most amazing things that I have come across. This table here that draws these contour maps. Here is either a satellite or surveyors go out and measure these, and all these lines on here, this little device, you just run it across there. Underneath is sensitized, and the digits go right through this cord into the computer over here and is stored. And all I have to do is just put it on this machine, and the whole map is drawn just like that on the computer. There are examples of that over here on this board here, and you can get three-dimensional layouts and okay. And back over on this board here, we have examples of other kind of graphic art that you can do. And I call it art. It's actually the physical representation of topography, right? And there's another type of readout. I don't know if that's a liquid or what it is, but the president of this company should be here now to describe that. Maybe we should call him in. All right. Well, while we're calling him, we'll talk for a second. Yes, now the president of this company, Dynamic Graphics, is right here for us to learn about this machine that actually makes the contour maps that I tried vaguely to describe. Now, how does this thing work anyway? This table with the contours and underneath and...
Okay, this is a table. This machine is kind of the inverse of the plotter.
You have the map that's already drawn.
We have a map drawn, and there's wires under this table.
Wires.
There's a magnetic coil under this cursor, and as you press the button, it can, within 0.005 of an inch, measure where the little crosshairs are located on the map. We can take and read the locations of contour maps along the contour lines and find out the XY coordinates along the contour lines. We can enter in over on the keyboard the elevations. Given the locations and the elevations, we can have the computer develop the shape of the surface represented by this contour map.
Mm-hmm.
We then do another contour map that shows the contours after they've done a development and they've cut away dirt and added dirt. And then for each area, we can tell the number of cubic yards taken away or added.
Yeah. So, but it looks just like the marbleized map. If I took one of my marble maps and put it on there, we can actually draw the marbling.
These are all lines of equal height.
And that's a contour.
visit contour. Once we have the surface level, we can either make, hold it.
Let's go back here.
Not quite yet.
It's going to be very soon.
Okay. Once we've entered the surface definition into the computer, we can have the computer draw out its own contour map. And we can have the computer make a pictorial representation of the shape of the surface.
Very good. Now, I think the machine is coming right up on making the brightest star Sirius, so you can actually come pan right over here and start watching it happen, which is going to be very soon now. And you can come closer, and we'll open the box. I'm going to step in front of the camera, if you don't mind. Excuse me. Thank you very much. And
Don't hit those buttons.
oh no, I won't. So we're going to open this up now, and or shouldn't it be open while the Sirius is going
Well,
on?
okay. I would suggest cutting until it comes up because you may run 5 minutes of film with nothing.
You don't think it's going to be this soon yet, huh?
Well, it'll take long enough to draw the big star that you can click your camera on. Let's just be ready.
All right, now we're going with Sirius, the brightest star, and see that thing going around and around, and it's filling it in, filling the dot in. And now the magnitude of the Sirius is minus 1.45 visual magnitude, and the minus numbers are the brightest, and the plus numbers are the dimmest, like nail gauge, is the way they go. And for each jump in magnitude, it increases about a little over two and a half times as bright. And of course, every time you double or increase one magnitude, it doubles the number of stars. And this is now Sirius is drawn. Now there's another star that's being drawn. It's probably right on top of it that we can't see. Maybe it's the companion of Sirius, who knows. And pretty soon, it'll start drawing the stars of Orion, which on this half of the sky will be all the belt stars. The top belt star rests just very close to the celestial equator. And as a matter of fact, you could probably pan up to the map through the other room. Could you see the map in the other room? That bright star in there is Sirius. Art?
Let's go back to it.
We've seen Sirius there, and if we pan back up and look at this map in here, you can see the bright star there is Sirius, is what it's drawn. And now I'll tell you, the reason it's doing it this way is it's doing each star in it. No,
No, just stay out of the way.
Okay, now there's Sirius, the brightest star, and I'll show you the way it looks on this map in here. It's the brightest star there. The belt stars of Orion point down to it. And in just a few seconds, well, actually it isn't, because that's about 10 or so minutes away to get into Orion by the computer. And I was trying to expound like this, it's...
Well, if you'll notice the way the stars are being plotted on this, it's moving back and forth, and the order of the stars has been chosen so as to minimize the amount of travel time in the plotter pin from one star to the other. And if you were to do them randomly, of course, you would spend a lot of time on the plotter traveling from one star to the other. So the stars have been what I call strip sorted, so that it minimizes the amount of distance it has to move from one star to the other.
And this is, as I said, the Yale Bright Star Catalog.
Start again.
Okay. All these stars are from the Yale Bright Star Catalog from the Yale Observatory, and of course they rely on other observatories, let's say in the southern hemisphere, to bring their collection of coordinates together and publish their list. Other observatories have their own lists, some publish, some not, and we're using the Yale. There have been books written about the accuracy of various catalogs, and Yale doesn't rank near the top, but more and more uranographists, people who graph the universe, are using the Yale catalog because essentially for star maps we're interested only in the naked eye sky, the stars that ordinary people can see and to use to find their way or to stargaze or to learn the constellations. And my whole interest is the star lore that the ancients, you see, we're seeing living history itself. When we look out into the sky, we're seeing what the ancients saw. And so I'm primarily interested in all the naked eye stars. And this is almost the extreme limit. That one that we had out in the hall there, what I call my award-winning map, I entered it in a map design competition by the American Congress on Mapping and Surveying, and it won along.
Go ahead. It went along.
Okay.
It went. start with it went along.
Okay. You're not on. Oh, you are? Yeah, it went along. No, I forgot.
It went along with
Oh, yeah. They, along with my award winning was the CIA satellite. Oh, the next brightest star. You can just pan right over here for a moment. That's Canopus. It means the chief pilot of the fleet of Menelaus, which is in the ship Argo, the ship that carried Jason searching for the Golden Fleece. The whole constellation of Argo, the ship, was broken up by the Astronomical Union into three: Pupus, the poop deck of the ship; Corinna, the keel of the ship, which Canopus is a part; and Vela, the sails of the ship. But on this map here, as I say, there's 5,700 stars. There'll be well over 6,000 on this one, and on the monster map that we saw earlier has 8,602. That's the extreme limit of naked eye visibility. Now that we've seen this computer in operation in the room, I'm going to go out and summarize and see what we've done in our operations today. Come back to our award-winning map right here, which is the first computer map I drew back in 1972. And all these maps are representations of the celestial sphere. Unlike terrestrial geography, where we must go to the spot on the map to appreciate it, with a celestial map, you can be any place on Earth and the stars just come to you. You can just stay put, and one night the whole sky will roll around, especially at the equator. But all these are flat representations of a sphere, and no matter what you do, there's always going to be this distortion, either at the top or the bottom, or if you make another projection like the spherical ones, it'll give you a distortion another way.
sort of like a Mercator projection versus a
Yeah, this is like a Mercator,
drop.
but this is a straight cylindrical with each degree being equal. Each degree is equal both in latitude, or what they call declination, and longitude, what they call right ascension. And
Hold it.
okay.
Okay, now this is up. What is it? Explain the up again.
Yeah, this is the equator, and this is the southern and
Okay, now you're
northern
getting my
hemisphere.
shot.
Oh, excuse me.
Remember, like I say, don't point anything unless you don't. You see, all I got is your hands all over the map. So
Okay.
do it again now. Go.
Yeah, so no matter what representation you make, a flat surface will always make some distortion. And this is how I got started in celestial map making to begin with. Came home from the 1970 eclipse and found that the National Geographic put out a circular star map, what I call made for people that live at the North or South Pole. The poles were centered. The circumference was the equator, and you have to piece the equator together in your mind to get bearing. And anybody in North America looks out, the equator is halfway up in the sky. So everybody knows what's in the north because they can see it anytime they want to. It goes round and round. But when they look south, they miss all this beautiful stuff, the flow of the ecliptic and the wintertime wonders and the whole lay of most of the sky is when they turn south.
Now, what is this? Is even and this is not. Can you explain that? Even divisions, even.
Yeah, each degree is equal both in latitude and what we call right ascension. This long line here is what they call right ascension. It's the stars move this way. It's actually us that's doing the moving. We're rotating every day and revolving about the sun and rotating around the earth. And after I saw the National Geographic map, I thought I'd have to make my own, and I conceived this rectangular or cylindrical projection. And by standing at an angle, of course, you can look at it and see the northern and southern hemisphere stars coming into their own, because just like you see the stretch stop in the street, when you look at it at an angle, it looks right, but then straight on, it looks all stretched out, and that's the way these do here. So you can make this any way you want, but no matter what way you do it on a flat surface, there's some distortion. And celestial globes aren't appropriate because for a celestial map, we're inside the globe looking out, and everything on the globe would be reversed. They have all these globes on sale, but the whole sky is reversed from the way it is on the globe. So that's why we're doing this. And to minimize some of this distortion, our new map is, these maps here are curving with an elliptical top and bottom so that the stars point up to the north and the Little Dipper curves around. And, this is uranography, graphing the universe.
Let me
Okay. Yeah, now this, what we're looking at.
wait. I haven't cued you yet.
Oh.
Go.
Okay, this is the area, what they call the wonders of the wintertime sky. You see Orion, the brightest star is Sirius, that's pointing down to it, Orion, the belt stars, and Capella on the very top, and Castor and Pollux, Gemini, the twins. And the belt stars of Orion point up to Aldebaran, which is the eye of Taurus, the bull, and the Hyades, which are the half-sisters of the Pleiades, right at the, just above it there. And all these stars you can see tonight, December, coming up. They come up early in the fall in the early evening and then stay out all winter. But in the summer, if you get up in the middle of the night or toward morning, you can see them then too. And then moving this way,
You would say that again?
yeah,
Ship, this is the one?
yeah, this is the ship Argo that carried Jason and the Argonauts. It is now comprised of 3 constellations, which the Astronomical Union broke it up many years ago because it was so big and unwieldy that when they were getting to dimmer stars than what you can see with the eye alone, they couldn't manage the numbering, so they broke it up into Pupus, the poop deck, Corinna, the keel, which has Canopus, the second brightest star, and Vela, the sails of the ship. And just above it, Pyxis, or Pixis, is Latin for box, but it means the ship's compass box, or it also was Molus. It used to be part of the sails of the ship. The mast, Molus, the mast. Area where the sun is right at September 22nd, right in the middle of the map, the autumnal equinox. Of course, the opposite time of the year is a very interesting part. At the top we have the Dipper that arcs to Arcturus, and then down to Spica, and then further down, but up here and on this right side is the Nebula and Leo the lion. The Nebula is the tail of the lion, and further on east here, Regulus. And halfway between Denebula and Spica is the wings of the Virgin, or also known as the dog kennel. And halfway between Denebula and Cor Coralie, which is right under the Dipper, is Coma Berenices that was
Where's
named
that
by
now?
Coma Berenices is right there.
Go ahead, point it. You can point to it.
Right
I don't
here.
mind if you point. It's just move your hand out when you're finished.
Yeah, and that's a field of galaxies, and the telescope and time exposure photographs, that whole area fills up with lots of galaxy shapes and different perspectives.
Okay.
And now we'll move on
Point
to
another one.
Diamond of
Wait,
Virgo.
wait. Okay.
Is Cor Coralie, Arcturus, down to Spica, and over to Denebula, this large diamond here.
Describe the diamond again, or with your hand.
Yeah, the diamond goes like this to Denebula, and then up to Cor Coralie, and then back down over to Arcturus, like that. And now we'll move.
Again.
Yeah, this is the area of the summer triangle. You see Vega, Deneb, and Altair, and Aquila the eagle, Lyra the lyre, and Cygnus the swan up on top. And here's Ophiuchus, the head of the serpent bearers, Ras Al Gadi. Ras Al Hague. Ras Al Gadi here is the head of Hercules. He's upside down. Here's his knee. He's known as the kneeler in Arabic, and that's his hand holding Cerberus, the 3-headed dog. And the other constellations of this area: Sagitta the arrow, Delphinus the dolphin, also known as Job's coffin, Equuleus the little colt, next to Pegasus the flying horse. The head of the horse, the neck, and the wing. This is the horse that Perseus rode after he cut the head of the Medusa. Its blood spilling to the ground changed into Pegasus, and he rode off and saved Andromeda from Cetus the whale.